Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on November 14, 2025, about 3 days ago. It introduces a way to get wider representations without the quadratic compute cost, showing that an 8 times virtual expansion accelerates optimization by over 2 times for next token and 3 times for next 2 token prediction. The paper is titled Virtual Width Networks, and as we'll see later, the implications for model training efficiency are quite significant. So, figure 1 shows that an 8 times virtual width speeds learning without extra backbone cost. Next 2 token prediction means the model predicts 2 upcoming tokens jointly, which stresses short-range composition. The left graph charts next token loss, where the virtual model reaches the baseline using about 2.5 times fewer tokens. The middle graph reports next 2 token loss, with roughly 3.5 times fewer tokens. The right graph shows downstream accuracy higher by about 2.2 points. Alright, figure 2 contrasts 3 layouts to show why virtual width helps without blowing up compute. The left panels depict a standard transformer and a naive wider version, which both tie embedding width to backbone width so cost grows quickly. The right panel introduces virtual width, which keeps the backbone narrow while embeddings are wider. Generalized hyper-connections act as lightweight routing that compresses to backbone size and then expands back, so representation grows with minimal overhead. So figure 3 lays out how virtual width actually flows through the model. The left panel contrasts a standard transformer that keeps one width everywhere, which forces compute to grow fast when widened. The middle panel shows virtual width routing with generalized hyper-connections, which are small projection paths that compress to backbone size and then expand back so representations stay wide without heavy cost. The right panel adds multi-token prediction, meaning the model learns from several future tokens at once, which strengthens token representations. Alright, figure 8 shows the scaling law that ties virtual width to lower loss. A log linear fit captures the pattern, which means doubling the virtual width reduces loss by about 0.007. The red point at r equals 2 marks the first observation on this curve. The red point near r equals 8 sits lowest, consistent with the steady decline indicated by the fitted blue line. So figure 8 showed a log linear trend. Table 1 confirms the concrete gains. Table 1 summarizes results at a fixed fraction rate, m equals 8, which means the hidden state is split into 8 partitions. VWN times 2 reduces next token loss by about 0.020. VWN times 4 cuts next token loss by about 0.028. VWN times 8 trims next token loss by about 0.035. Accuracy improves by about 4 points at the highest setting, and next 2 token loss drops by about 0.058. Okay, 2 takeaways stand out. Virtual width decouples representation size from backbone compute, so models learn faster with modest overhead, and the gains scale smoothly with each doubling of virtual width trimming loss by about 7 thousandths. The broader implication is a new practical axis for efficient capacity scaling. That is it for the AI Research Roundup. I am Alex. Thanks for listening.